So it's a pleasure to introduce Natalia Porqueres. Natalia did her PhD at the Max Planck Institute for Astrophysics. And then she did a postdoc at Imperial College. And now she's moved to Oxford University as a Beecroft Fellow. All her work is on cosmology and large-scale structure and specific topics like weak lensing. So take it away, Natalia.
Thanks, Mike, for the introduction. And thanks also for inviting me and having me. So I will present a field-based approach to analyze weak lensing at the pixel level that allows us to extract more information from the data. So let me introduce first cosmic shear. So when we observe the distant galaxies, we don't see them as they really are. We see them slightly distorted, because when the light from the galaxies travels to the Earth, it's deflected and bended by the gravitational potential of these large-scale structures. So we don't see the galaxies with the shape they really have. We see them slightly distorted. In practice, that means that when we actually look at the projection of the galaxies on the sky, if we could see also the dark matter, we would see them aligning, or if they seem to align with the large-scale structures and all this filamentary structure of the cosmic web. So we start with some galaxies that are randomly distributed, and then due to the gravitational lensing effects, they show some, we observe them as showing some slight alignment, some preferred direction. So if we take all these galaxy images and average the shape of these galaxy images, then we get an estimator of the shear. And this is a very powerful probe to analyze the dark matter distribution, make a map of the dark matter distribution, and get a better understanding of dark matter and dark energy. So in practice, things are a bit more complicated because nearby galaxies are going to feel the same gravitational potential, and then they will have some alignments that we call intrinsic alignments, but I'm going to come back to this later. Okay. So the standard approach to analyze all these galaxy images is to take all the galaxy shapes and compress them, summarize them into a set of functions. Very often only the two-point correlation function or the power spectrum. So studying correlation functions and power spectra has brought us a long way in cosmology. But now, with the new surveys coming in the next few years, we need to start asking the question of whether doing this, compressing all the galaxy shapes into just two-point statistics, can we capture all the information that is there in the data? And the answer is no. The standard approach misses a lot of information. So as an illustration here, you see two fields that are clearly different by eye. One of them is a simulation of the cosmic web, and the other one is just a Gaussian random field. But if we measure the two-point statistics of these fields, they have exactly the same power spectrum. So if we only measure the two-point statistics, we would not be able to distinguish which one is the cosmic web and which one is just a Gaussian random field. So this shows us that there is much more information in the data than what the two-point statistics can capture. And if we want to make full use of the data, we need new techniques. So in the near future, we are looking at a very bright future because we are going to have very high quality data. So the upcoming surveys are going to provide huge volumes of data with very, very high quality. This is great because then this new data will have unprecedented statistical power and much smaller error bars. And that means we are going to be able to get a better understanding of dark matter and dark energy. There's a great potential for discovery, but that also means that the existing methods are reaching their limits, especially the standard approach is reaching the limits in the amount of information that it can extract from the data and the physical modeling also. Also, since we are going to reduce the error bars in the data, that means we will need very, very good control on the systematic effects. So the new data sets are going to require new...
What's that? Thanks, bud.
Sorry? Is that a question or?
No. Sorry, random noise.
Interruption.
No worries. Okay, so the new surveys or the upcoming surveys are going to require new data analysis techniques that we need to actually make full use of the data and extract all the information that is there in the data. So how can we extract all this additional information? So one way to do that would be to use high order statistics. So in this case, we would keep compressing the data, summarizing the data into a set of functions, but adding higher order correlation functions, for example. So that would allow us to extract more information from the data and get complementary information to what the two-point statistics can do. But there are some questions here that we don't know what the sampling distributions of these quantities are. And even if we assume that they are Gaussian, then the question is, how do we compute the covariance matrix in an accurate way? Another problem here is that we don't know when to stop. We can always get new high order statistics, and we don't know at what point we have exhausted all the information that is there in the data. So as an alternative to this, we have a field-based approach, which is a much simpler idea from the point of view of physics. So the idea of a field-based approach is directly analyze the data at the pixel level without compressing it into summaries and correlation functions. So this brings me to the outline of the talk. So I'm going to first present the method, the field-based approach for weak lensing. I'm going to then show the proof of concept. We did some tests with simulated data to see what's the constraining power of these methods, how much we gain from going to the pixel level. And then I'm going to describe the challenge of getting ready for the real data application. So how does a field level approach works? So the first thing we have is we have some cosmological model. And then given some cosmology and a model, we can predict some shear fields. And then we will compare these predicted shear fields to the data directly at the field level, doing all the statistics pixel by pixel. And by doing this, by doing statistics pixel by pixel, we can in principle get all the information that is there in the data. Now, to generate these predicted shear fields here, we need a forward model. So we need to run simulations. And in this case, we are dealing with a probabilistic forward model because the simulations that we use are constrained by the data. So in contrast with what one would do in a machine learning approach, in which one would run many simulations and then use this to train the neural network, what we do here is to only run the simulations that can plausibly lead to the structures we see in the data. So we only have simulations that are consistent with what we observe. And that means at the end, we are going to get a map of the dark matter distribution in the universe that is inferred from the observations. Okay, so to do this, I use the Borg framework. Borg stands for Bayesian Origin Reconstruction from Galaxies. And this is a Bayesian framework that allows us to have forward models. And the important thing here is that Borg has a gravity model. And that's important if we want to capture all this filamentary structure of the cosmic web. So that's how the forward model for Borg looks like. So the first thing we do is to sample cosmological parameters from a uniform prior. And then we build a box of initial conditions. So we know that the initial conditions in the universe are well described by Gaussian statistics. So here we use a Gaussian prior. And this is connected to the cosmological parameters through the initial matter power spectrum. Then we evolve these initial conditions in time using the gravity model that also accounts for the light cone effects, and that gives us the evolved dark matter distribution. And now we have all this filamentary structure of the cosmic web, and now we can integrate along the lines of sight and apply the lensing model, and then we will get the shear fields. So in this step, we are going from a three-dimensional box to several two-dimensional fields that are projections on the sky for different redshift distributions, different redshift beams. So here, I should say that we are actually getting the reduced shear rather than the shear. So we compute the convergence field, and from there the shear in the flat sky approximation, and we operate on the reduced shear because that's what we actually observe. Okay, the last step we need to take here is to account for survey effects, like, for example, masks. So there are regions of the sky that are not observed. There are stars that block the light from distant galaxies. So we need to account for this. And this is very straightforward to do with the field-based approach. So if you have a masked pixel, you just give this pixel an infinite variance, and that's it. Okay, then we will compare these predicted shear fields to the data. But with all these forward model here, the sensitivity to the cosmology is threefold. It depends on the cosmology through the initial matter power spectrum that gives us the covariance of this Gaussian prior for the initial conditions, through the growth of structures, which is encoded here in the gravity model, and through the geometry, because every time we change the cosmology, the distance redshift relation changes, and that means the line of sight integration here also changes. So all these quantities change consistently when we sample the cosmological parameters. Everything is updated consistently throughout the forward model, and that's what allows us to constrain cosmological parameters with this forward model. Okay, so once we have the predicted shear fields, we compare them to the data pixel by pixel. So we have a likelihood that runs over the different tomographic bins, the different redshift bins here, and over the different pixels on each one of these maps. So here we have the difference between the data and the model that comes from evaluating this entire forward model for the two components of the shear. So here we are assuming that the noise in the pixel is Gaussian. So we assume that after we average the shape of the galaxies in the same pixel, the noise in these big pixels that contain several galaxies is going to be Gaussian. So one advantage of this type of methods also, yeah.
Oh yes, sorry. Can I ask, so in your expression for the likelihood, it looks like you're assuming that the covariance in this shear is diagonal. Is that right?
Yeah, right. So that was my next point. So
oh, sorry.
No worries. Since we are the likelihood operates on the noise, we can assume here that there is no covariance matrix, or that it's diagonal, because the variance of the noise in each pixel is going to be given by the number of sources, the number of galaxies that we have in that pixel. Now in practice, okay, so in practice, this is not 100% true, because we have intrinsic alignments, right, that will introduce some correlation between the pixels. But instead of modeling the intrinsic alignments as a noise term, we actually model them as part of the forward model. So I will come to that later in the talk. We are going to introduce this as part of the signal. Okay. So what we want to do here is to sample cosmology and initial conditions simultaneously, because we need to be able to compare to the data. So in practice, in terms of probability distribution, what we want is the posterior distribution of the cosmological parameters and the initial conditions given some data. Now we can apply Bayes' theorem, and then we will get this. The first term here is the probability of the data, of observing some data given the model. That's basically the likelihood that I just described. The second term is the probability of the shear field having some shape given some initial conditions. And that's the forward model. And the forward model is mostly gravity and integrations along the line of sight. So the forward model is deterministic, and that means it's just a Dirac delta here. Then the next term here is the probability of the initial conditions given the cosmology. And that's the Gaussian prior that has a covariance matrix that is basically the power spectra of the initial conditions. So that depends on the cosmology. And the last term here is the prior on the cosmological parameters, which we just use a uniform prior. Okay, so in practice, we want samples of this posterior distribution. So our results are going to look something like that. So this is a movie of the samples that we get from the posterior distribution. You can see here the cosmology changing and also the initial conditions changing. They don't change very much because this is a constrained run, so this is already informed by the data. But they oscillate, and then in this third panel here, you see how changing the cosmology and the initial conditions affects the dark matter distribution. So it moves the structures around and it changes the amplitude of the structures. So as you probably anticipated, sampling the initial conditions is a very challenging problem because it means we are dealing with millions of parameters. We want to know the value of the density field everywhere in this image. So that means the value of the density in each pixel is a parameter that needs to be sampled. So in a normal analysis, we are dealing with millions of parameters, and to be able to do this in an efficient way, we use Hamiltonian Monte Carlo techniques. So Hamiltonian Monte Carlo basically uses information in the gradients of the posterior distribution, and these gradients allows us to inform or to explore the parameter space efficiently because it has some information on the geometry, on the landscape of this probability distribution. And the other advantage is that Hamiltonian Monte Carlo techniques use conserved quantities, and that guarantees a high acceptance rate. Okay, so we use Hamiltonian Monte Carlo for the density field because these are many parameters, but then for the rest of the parameters, we use a simple MCMC. So we use a simple MCMC for the cosmological parameters and then for the nuisance parameters and systematics. The reason why we split this problem into two sampling blocks is because we would not know how to define an efficient mass matrix. We would not know how to define how changing one parameter in the cosmology affects each one of the points in the density field. So we would not know how to define an efficient mass matrix. So it's much easier, more efficient to split the problem into two sampling blocks here. Okay, so now I will present the proof of concept, but are there questions about the method?
Sure. One thing I was just wondering was about the simulations. So are your simulations just purely dark matter only?
Yes, so for the proof of concept, I'm going to show, yes, now we have extended this with some baryon correction. I will explain this towards the third part of the talk in the chat.
Great, thanks.
More questions? Okay. Okay, so we did a proof of concept with simulated data. So what we want to see here is what's the constraining power of this method. So we simulated some data in a box that is 1 gigaparsec square on the sky, 4 gigaparsecs in the line of sight. This corresponds to 16 degrees squares and 13 arc-minutes of resolution. Now, we use 4 tomographic bins. So these are just Gaussian redshift bins distributed between 0.5 and 2. That is what this box covers. Then we added Gaussian pixel noise that has 30 sources per square arc-minute. That's what corresponds to what is expected for Euclid. And then to generate the data, we use Lagrangian perturbation theory. So this is dark matter only. And we use LPT. And we use the same model to generate the data and to analyze them. So this is a self-consistent test. And what we want to see is how much we gain in an ideal scenario. So we are going to analyze this data with Borg and with the standard approach with the power spectrum. And these are the results that we get. So here you see the constraints of on omega matter and on sigma 8 that we get from analyzing the same data, just using different techniques to analyze them. So when we use the power spectrum, we get this orange contour that is this typical weak lensing banana degeneracy. And then when we analyze the same data using Borg, we get the blue contour. So Borg can leave the weak lensing degeneracy and get more precise constraints on the cosmological parameters in this experiment here with the resolution that we use. The marginal errors of omega m are reduced by a factor of 5 and sigma 8 by a factor of 3. So this is very exciting. We can get more precise constraints on the cosmology from the same data, just changing the techniques we use to analyze the data. But we also here, another data product that we get, and it's also interesting, is the projection of the density fields. So we are also inferring initial conditions and density fields. So I'm showing here are the initial conditions and the convergence, which is the projection of the density field on the sky. The first column are the true fields, the ones we use to generate the data. And then here we have the mean and the standard deviation from the posterior samples. So if you compare the first two columns, you see we are recovering the structures from the truth. And we also have a way to quantify the uncertainty. So this field here, the mean convergence has a bit smoother structure than the truth, but that's just an effect of computing the mean. If we look actually at individual samples in the initial matter power spectrum in the 3D, we actually recover the correct power spectrum for the individual samples. Okay, so these initial conditions here are just from mock data. But when we apply these to real observations, we are going to get maps of the dark matter distribution that is there in the universe, constrained by the data. So there is a lot of physics that we can do with this dark matter distribution. So we can use them, for example, to study galaxy environment or supernova environment. We can cross-correlate them with the CMB to study TSZ effect. We can as well use the initial conditions to run constraint simulations, and then these hydrodynamical simulations would correspond to, or we would have the coordinates of the objects that we see in these hydrodynamical simulations, because this is inferred from data, so it should correspond to the actual universe. And we can as well use it, for example, to constrain dark matter annihilation models. So these are some of the projects that have been done with inferred density fields that have been obtained with the Borg framework, in this case for galaxy clustering. So there is a lot of physics we can do with these density fields, but they are also a very powerful tool to actually check our data. They are very powerful for cross-validation. So one thing we can do with the density fields is to do posterior predictive tests. So here we are back at the proof of concept experiment. So this was how the data looked. This is the second column is the truth for the two components of the shear. And then we can, the other columns are the results of the posterior predictive test. That basically means we take all the quantities that we inferred, like the density and the cosmology. We apply the forward model to them and see whether we can actually recover the truth, whether our inferred quantities can explain the data. And here we computed the residuals between the truth and the posterior predictive test, and we see that for this proof of concept, the Borg was able to infer the quantities and or the inferred quantities can explain the data at a subnoise level. So here we have the residuals of the inference of the posterior predictive test, and the green line is the distribution of the noise. And we find that the residuals are narrower than the noise. So of course, in real data, we are not going to have this second column here, but we can still use these density fields to cross-validate our results with independent measurements. So when we apply this to real observations, we are going to see, we're going to get a map of the dark matter distribution on the sky. And then we can use this map to ask questions and see whether our results are consistent with what we know of the dark matter distribution. We can ask it, for example, whether the clusters that we know should be there are there. In this case, we knew that the coma cluster should be in this area. So we zoom in here and we found the coma cluster with a number of filaments that were expected for this cluster. So here there was no prior or no additional information for the position of the coma cluster. This is directly inferred from the data. And another question we can ask to validate our results is whether we get the expected mass profiles for the clusters. And this test was done by Jens Yashan Gildabo, and they found that the mass of comma cluster, which is this red line inferred by Borg, is consistent with independent observations. We could, of course, do the same kind of test for the initial conditions and compare them to the CMB. So all these infer maps are also an interesting way and a powerful way to cross-validate and test whether the results that we are getting are consistent with independent observations. Okay, so I'm going to now say, just briefly say what's the current status of Borg. So I have mentioned that there is Borg for galaxy clustering. I have been describing the Borg module for cosmic shear. We also now have velocity tracers, and we also have a module for Lyman alpha forest. So we could, in principle, combine all these data sets with Borg and generate maps of the initial conditions of the universe, of the dark matter distribution, velocity fields, and constrain the cosmology. So the current status of this is that the galaxy clustering has already been applied to real data, and the rest of the modules are in proof of concept stage, but the cosmic shear is moving towards real data. So when we can do this, when we can apply the cosmic shear to real data, then we will be able to do a multi-probe analysis at the field level. And this will give us better constraining power, but it will also give us a more robust way to analyze the data, because different data sets are going to have different systematics, and combining them is going to give us more robust results. For example, the cosmic shear can put some constraints or can break some degeneracies to get a better constraint of the galaxy bias. So now to move towards real data, there are some challenges. Here we need, there are 3 points we need to address before we can apply to real observations. First is we need a more realistic gravity model. Lagrangian perturbation theory is not going to be enough. We also need to incorporate astrophysical systematics like intrinsic alignments and baryon feedback. And we also need to account for survey systematics like calibration effects and so on. So the first 2 points we already addressed, and we still work in progress for the survey systematics. So let's talk first about the more realistic gravity model. So we already have in Borg a particle mesh. So this has already been used in real data analysis to analyze the 2M++ galaxy clustering. So these are that you're seeing here are some of the results. The red dots here are the galaxies from the data. And this is the dark matter distribution obtained from the particle mesh. So we have a better gravity model that allows us to go to 2-3 megaparsecs of resolution. Then the next point is.
Can I ask you a question?
There's a question. Hang on.
Sure.
You might have to stand up. There's a question.
Can you hear me?
Yes.
Yeah, so could you kind of compare the new gravity model to the old gravity model? I guess I don't remember. I mean, how is the new gravity model different from the old one?
Okay, so the one I described before, the LPT, is basically Lagrangian perturbation theory. This is an approximation that would break down at like a 10 megaparsecs or something like that. So for the proof of concept stage, which we use very coarse resolution, that was enough, but it's not good enough for the small scales because it has shell crossing and so on. So for using the data to analyze data at high resolution, what we need to do is to go to much smaller scales, and for that we need a very accurate gravity model that needs to do several time steps and so on. So this is a much more complicated gravity model that has 2 steps in which the gravitational potential, we compute the gravitational potential, move the particles around, update the gravitational potential, and so on. And in the other case, this is just a 1 time step thing. So we have initial conditions, we compute displacement fields, and we evolve the particles.
Thank you.
Are there more questions?
No more
Okay.
questions.
Okay. Okay, so this is the forward model that we had. And here we are missing intrinsic alignments, which we now have added. So we have the dark matter distribution, and that means we have access to the tidal field. We can just compute the tidal field here. And from the tidal field, we can compute the intrinsic alignments. We can do that in the 3D, and then we average them on the line of sight. So we incorporated the TAT model that accounts for tidal torquing and nonlinear alignments of the galaxies. And we incorporate these here. And then basically our predicted fields here are going to be the shear fields that include intrinsic alignments signal. The other model that we are missing here is baryon feedback. So what we have done is to incorporate baryon feedback at the field level rather than doing some correction of the power spectrum. So what we did is to implement the Dayan-Selyak model. So this is it's a displacement field that we use to correct the position of the dark matter particles, and then this will correct for the baryon feedback. So adding these two models, adding intrinsic alignments and baryon feedback, requires also some more sampling parameters. We have 3 parameters that we need to sample for the intrinsic alignments, and the baryon feedback also has 2 parameters that instead of calibrating them to some hydrodynamical simulations, we are going to directly sample these parameters of the baryon feedback model so that we can marginalize over them and they are directly constrained by the data. So for intrinsic alignment, yep.
Yes, I mean, can you just describe in more detail what these parameters are?
Yeah.
Like it seems surprising to be able to even approximately capture baryonic physics using like 2 parameters only.
Mm-hmm. Yeah. So this is how the baryon feedback looks like. So this is the displacement field that we use for to correct the position of the dark matter particles. So we have the density field. This is the dark matter only density field. Then we have a smoothing operation here at the gene scale, the gradient, and then here we have some constants and coefficients. The parameters that we sample are this beta that controls the amplitude of the baryon feedback, and the gamma that is connected to the equation of state of the gas. So these are the 2 parameters that we sample, and this is basically the model of the Dayan-Selyak, which is basically a particle gradient descent. The idea is that gravity is a minimization problem, so we can just use gradient descent to approximate these effects.
Okay. Like is the idea, I guess, just that like your simulations have such a low resolution that this sort of simple approximation is good enough? Yeah.
Right. So for the resolution of the proof of concept, we are not even able to constrain these parameters because the baryon feedback is not significant. It's not important at that scale. But for higher resolution, we want to be able to measure this and to constrain this. But we are not going to go to a kiloparsec. So we are going to stay like around 1 megaparsec, and this model should be sufficient around 1 megaparsec.
Really, 1 megaparsec? I mean, okay, that seems ambitious, for such a simplified model. Okay, and then similarly for your tidal model, can you describe that a bit?
Yeah. So so this is we use the TAT model, which includes the tidal alignment and also the tidal torque. That means we have terms that are proportional to the tidal field and terms that go with the square of the tidal field. Now we have these coefficients. There are these 3 coefficients here. We have they have some parameters. So they depend on the critical density of the universe and so on, and they have some parameters that we sample. So these are the 3 parameters that we sample. This is at the resolution of the proof of concept that I show. So we are able to constrain A1 and A2. BTA, that would be the one that enters here, that is proportional to the density field. We don't seem to be able to constrain. We're just recovering the prior distribution here. So for comparison here, there are, this is an update on the cosmological parameters when we introduce intrinsic alignments. So these are 2 self-consistent runs. So we are not analyzing the same data here. What I'm showing here is how much information we are getting from the intrinsic alignments. And we're getting a bit maybe of information on sigma 8, but not much on omega n. It seems to broaden the contour a bit here.
I see. And this sort of model matches well to like full hydrodynamic simulations where you actually form galaxies.
Right. So this is the best model that we have. But it has not been tested at the field level, so we don't know whether this will be sufficient. We are going to experiment with this first, and then the question is actually, what if these models are not good enough, right? So both the intrinsic alignments, so both the intrinsic alignments and the baryon feedback have been tested at power spectrum level, and visual comparisons also with the density fields, but they have not been tested for inference at the field level. So what if these models are not sufficiently accurate? So in this case, what we would do is to go to use machine learning to help connecting the physical models to the data. So for that, we would use the approach of Tom Charnock that is called neural physical engines. And that means using a layer of neural network inside the Borg framework. And this is a not trained neural network. So that means there's no training data. We would learn the parameters of the neural network, meaning the weights and so on, directly from the data themselves. And by doing this is a fully Bayesian way of using neural networks within an MCMC framework and an inference problem. So this plot here is an example. They use this to increase the resolution of an embodied simulation. So these are the initial conditions, and this was the reference. So for the evolved density field. So this is what they use as like simulated data. So the resolution that they use in Borg in this case was this lower resolution density field. And then they train the neural network parameters, or they feed the neural network parameters, they infer them directly from the data without training data. And this is what they got. So they were able to reproduce the higher resolution or increase the resolution of the density field by doing this, by introducing a neural network as an additional layer in the forward model, and then directly infer the parameters of the neural network from the observations. So that's what a generalization of this is what we would use if our bias model or the intrinsic alignment model was not sufficient. Okay, so the last point here are survey systematics. So this is calibration and so on. This is still work in progress. So the first thing is we need robust redshift distributions, and they also come with some uncertainty, and we need to propagate the uncertainty of the redshift distributions to our cosmological results. So for this, at the moment, what we are using is just fixed n of z's, but ideally what we want to do is to use a Bayesian hierarchical model that samples the n of z's. It provides samples of the redshift distribution, and then we can incorporate that inside Borg and use the different samples, and then we would marginalize over the redshift uncertainties. So the idea of this Bayesian hierarchical model is to use a forward model where the parameters would be the height of these histograms. So we would infer the height of the histograms in the N of Z, and then we would use samples of these inside Borg. So this is still work in progress. And then the last thing is that with field-based approach, and this is a bit of a futuristic thing, but with a field-based approach is it should be relatively easy to account for inhomogeneities on the sky in the survey. So different observing nights have different seeing conditions, they have different weather conditions, and that means that the survey is not homogeneous across the sky. It doesn't have the same depth across the sky. So what you're seeing in this plot is the depth of the KIT survey in the footprint, and you can see that there are regions that are shallower than others. So this is expected to have like a 10% effect on the cosmological parameters for the case of KITs. And it's very, very complicated to deal with this in a power spectrum summary statistics approach. But with a field-based approach, it would be relatively easy to incorporate if we had a model for that, because we can use these templates directly on our data on the field. So we could identify shallower regions, and we could calibrate redshift distributions differently in different places, or treat them with different uncertainties. So this is a bit looking into the future, but this is something we will be able to do. So summarizing, there is more information in the data than what the 2-point statistics can capture. And if we want to make full use of the observations of LSST and Euclid in the future, we need new methods that can extract this additional information. And one way to do that is to use field-based approaches. And we have shown that the field-based approach can actually leave the weak lensing degeneracy and get more precise constraints on the cosmological parameters. So now the next step is to get ready for the first real data application of Borg lensing.
Thank you.
Happy to take questions. Thanks.
Natalia, questions? Alex has one behind me, just talk at the mic.
So when you say that there's a 10% effect of the survey systematics on the parameters, where does that come from? And does that mean that there's a large unmodeled systematic uncertainty in the cosmology results from kids for other weak lensing surveys?
So they estimated that it affects the error bars by like a 10% if you account for the depth. This is in this paper here.
So 10% of the error, not 10%
Of the error,
of
yeah.
the. Okay.
Right.
Any questions? Niesh, just talk loud.
So this plot you have over there, this was with your old gravity model, is that right?
Yeah.
So how does this change with your new gravity model? Or do you have something like this?
Okay, so for the new gravity model at this resolution, we would get more or less the same. It wouldn't be a big change, because at this resolution, the Lagrangian perturbation theory is a good approximation. But as we increase the resolution and there are more and more linearities, the particle mesh would give us, in principle, more constraining power.
Do you have an actual comparison that shows, or a plot that shows this, or not?
No, I don't have it at the moment. No.
Thanks.
I have a question. So if you wanted to do all of Euclid, for example, then you need a much bigger box than your test, right? Like maybe 10 gigaparsecs. And then you want to do it ideally at high resolution and run particle mesh rather than LPT. That seems like a lot of parameters, and it seems like a lot of computational time per MCMC step. So can you comment on that?
Yeah, so it's true that for this kind of methods, doing full sky is going to be challenging. What we are experimenting at the moment is to see whether we can actually split the box, the big survey, into smaller boxes and do this in parallel. And that would also save us that if there is some region of the sky where there is not much information, we can just keep that volume, for example. So the idea would be to do the very large scales at very coarse resolution and then that in a single box, and that we can do, and then split the box into smaller boxes that have these large scale modes, and then increase the resolution of the individual boxes, and then combine them together.
Okay, still sounds challenging.
Yeah, we're still experimenting with that, yeah.
Any other questions? Well, if there are no questions, let's thank Natalia again. Hope you can come and visit us in person one day,
Sure, yeah.
and then you could have pizza with us.